When we close our eyes and think about space, the image that most easily stirs both awe and unease is that of a black hole. These cosmic entities are not merely celestial bodies. They represent the extreme limit of physics as we know it, regions where gravity becomes so intense that no particle, not even light, can escape. From the first time they were theoretically proposed, back in the 18th century, to their observational confirmation in the 20th century, black holes have always held a unique place in the human imagination, that of a profound mystery and, at the same time, a silent threat. They are not like a visible comet streaking across the sky, triggering immediate alerts. They are instead invisible predators of the cosmos, hidden in darkness, lying in wait, shaping space and time around them without emitting any obvious warning to our senses. The fascination with these entities comes precisely from the combination of the unknown and the absolute power they exert. Over the decades, scientists, writers, and filmmakers have explored black holes as symbols of the unattainable. In popular culture, they are portrayed as portals to other universes, shortcuts for impossible journeys, or monstrous devourers of worlds. In science, however, they are the subject of meticulous study, challenging our most fundamental laws and putting to the test theories once thought unshakable, such as general relativity and quantum mechanics. The more we learn about them, the more we realize that we are only scratching the surface of a phenomenon far greater than we can comprehend. The fear, however, is no less real than the curiosity. The very idea that a black hole could approach our solar system triggers an instinctive alert. This is not a danger like a volcanic eruption or an asteroid on a collision course, which can be detected in advance and, in theory, deflected or mitigated. A black hole, depending on its trajectory and speed, could remain invisible until it is dangerously close, and its effects would begin to manifest long before we could even pinpoint its location. Its reach is not limited to destroying what it touches. It distorts orbits, alters gravitational fields, changes climates, and can rewrite the fate of an entire planet. It is important to remember that black holes are not distant and unreachable rarities. Our galaxy, the Milky Way, harbors millions of them, most roaming freely through space, unbound to any star. These are called rogue black holes, and they move like solitary travelers between star systems. The probability of one passing dangerously close to us is low, but it is not zero. And on astronomical timescales, even the rarest events become inevitable. Knowing this should not cause panic, but awareness. We live in a dynamic universe constantly in motion, where immense forces operate far beyond our control. If a black hole were to approach Earth, the subtlest signs could go unnoticed by the general population, but not by the instruments of modern astronomy. Even before it became visible due to the radiation emitted by the gas being pulled into it, we would detect changes in the orbits of distant objects, such as comets and asteroids in the Oort cloud. Small deviations, almost imperceptible, would reveal the presence of something massive and invisible in deep space. Science today has the ability to identify such clues, but the central question remains, what would we do if a black hole were heading our way? This question serves as the starting point for a journey that will explore not only the physics behind black holes, but also the possible catastrophic effects their presence could have on Earth. This is not an exercise in alarmism, but a scientific exploration of what would happen in the worst plausible scenario. We will dive into the origins of these entities, understand how they form, how they interact with space and time, and finally, based on real calculations and observations, imagine what would unfold if an invisible visitor, with the mass of several stars, crossed paths with our planet. This is an invitation to gaze into the abyss of the universe and try to understand with calm and objectivity what it can teach us about our fragility and our incredible capacity to observe and comprehend the cosmos. To understand the impact a black hole could have on Earth, we must first clearly and deeply grasp what it actually is. The scientific definition is straightforward. A black hole is a region of space where gravity is so intense that nothing, absolutely nothing, can escape its pull, not even light, the fastest entity we know in the universe. This fundamental feature makes it invisible to direct observation. We cannot simply see a black hole as we see stars or planets. Instead, we detect its presence through the effects it exerts on the matter and radiation around it. The concept of a body with gravity so strong that nothing can escape is not new. As early as the late 18th century, scientists such as John Michel and Pierre-Simon Laplace theorized the existence of dark stars, bodies so massive that the speed needed to escape their surface would be greater than the speed of light. However, it was only in the early 20th century, with the formulation of the theory of general relativity by Albert Einstein, that the mathematical framework to describe a black hole began to take shape. In 1916, physicist Carl Schwarzschild found the first exact solution to Einstein's equations that described a point in space with infinite density and an absolute gravitational field. This point, called the singularity, is surrounded by a boundary known as the event horizon, the ultimate limit beyond which no return is possible. The singularity is the core of the black hole, the place where all its mass is concentrated into an almost zero volume. The density is so extreme that the known laws of physics cease to function as expected. General relativity predicts that space and time curve infinitely at this point, while quantum mechanics, which governs the behavior of subatomic particles, cannot offer a definitive description of what actually happens there. It is in this region, where our best theories collide, that one of the greatest mysteries of modern science resides. Around the singularity lies the event horizon, which is not a physical surface, but a mathematical boundary. Anything that crosses it, whether a particle of light, a spaceship, or an entire planet, is irreversibly doomed to fall into the singularity. From that point on, time and space cease to hold the meaning we know. For an outside observer, any object approaching the event horizon will appear to slow down and freeze in time, becoming increasingly red as its light loses energy until it disappears completely. For whoever crosses this boundary, however, the fate is quick and inevitable, a plunge toward the center where everything ends. But black holes are not just wells of destruction. They also play a crucial role in the dynamics of the universe. In many galaxies, including ours, a supermassive black hole rests at the center, influencing the movement of billions of stars. These giants can have masses equivalent to millions or even billions of suns, and they are believed to have played a key role in the formation and evolution of galaxies. Smaller black holes, formed from the collapse of massive stars, are scattered through space, often as silent remnants of supernova explosions. Detecting them requires indirect methods. An isolated black hole with no surrounding matter is virtually invisible. However, when it interacts with its environment, pulling gas and dust from nearby stars, a spinning structure called an accretion disk forms, where matter is accelerated to extreme speeds and heated to immense temperatures, emitting intense radiation, especially X-rays. It is through this radiation and the unusual movements of nearby stars that we can map the presence of a black hole, even if it never appears in a photograph. By understanding the essence of a black hole, we realize it is not an object in the traditional sense, but an extreme condition of space-time. It is a physical and mathematical boundary between what we can observe and what lies beyond our capacity to comprehend. This understanding is essential if we are to imagine, based on science, what it would mean for one of these invisible colossi to approach our planet. The birth of a black hole is a rare event, but one of such violence and magnitude that it defies any comparison with phenomena known on our planet. The most common way they are born is through the gravitational collapse of a massive star, a process that occurs when a star reaches the end of its life cycle and can no longer support its own weight against the overwhelming force of gravity. For this to happen, the star must originally have a mass at least 20 times greater than that of the Sun. Over millions of years, this star consumes the nuclear fuel that keeps its fusion stable, a delicate balance between the pressure generated by reactions in the core and the gravitational force trying to crush it inward. When the nuclear fuel runs out, the internal pressure that held the star against collapse disappears. At that moment, gravity takes absolute control. The star's core collapses abruptly, compressing all its matter into an ever smaller region. In many cases, this collapse triggers a supernova explosion, releasing a colossal amount of energy and hurling the star's outer layers into space. What remains, however, is the true cradle of the black hole, a dense, continuously collapsing core that compresses until it forms a singularity, a point of infinite density surrounded by the event horizon. The birth of a stellar black hole is a spectacle that, although it occurs thousands or millions of light years away, can be detected by our instruments. The radiation from the supernova illuminates the galaxy for weeks or months, temporarily outshining even the brightest stars. But when that light fades, what remains is absolute silence, an invisible presence that can only be revealed by its gravitational effects. In binary systems, for example, the newly formed black hole may begin pulling matter from its companion star, creating an accretion disk that emits intense radiation and reveals its location. Not all black holes, however, are born from stars. Some formed in the very first moments of the universe, in the seconds after the Big Bang, when conditions were so extreme that regions of abnormally high density collapsed directly into tiny black holes, known as primordial black holes. These, if they exist, could have masses ranging from that of a small mountain to billions of times the mass of the Sun, and some may have completely evaporated over billions of years due to Hawking radiation. Another, even more monumental form of birth is the creation of supermassive black holes. The exact origin of these giants is still the subject of intense scientific debate. One hypothesis suggests that they began as stellar black holes, slowly growing over billions of years by swallowing gas, dust, and entire stars. Another theory argues that, under certain conditions in the early universe, immense clouds of gas could collapse directly into giant black holes without passing through the stellar phase. What is certain is that virtually all known galaxies harbor a supermassive black hole at their center, and the one in the Milky Way, called Sagittarius A star, has about 4 million times the mass of the Sun. The formation of a black hole is, therefore, the inevitable result of an extreme imbalance between gravity and the forces that try to oppose it. It is the absolute victory of gravity over every other physical force, a triumph so complete that it creates a region of the universe where even light is a prisoner. And it is precisely this feature, the ability to capture everything around it without giving any chance of return, that makes the approach of one to our solar system potentially devastating. When we talk about black holes, it's easy to imagine that they are all cosmic monsters of unimaginable proportions, capable of swallowing entire planets with ease. The reality, however, is more complex and fascinating. They exist in different sizes and categories, each with its own origins and characteristics, but all obeying the same fundamental law, a gravity so intense that nothing can escape its influence. Understanding these differences is essential to assess the potential danger each type could pose if it were to approach Earth. The most well-known type is the stellar black hole, formed from the gravitational collapse of very massive stars. They typically have masses ranging from 5 to several dozen times the mass of the Sun, despite being compact, with event horizons that may measure only a few dozen kilometers in diameter. Their density and gravitational power are unimaginable. A stellar black hole could easily destroy a planet like Earth if it came close enough, even without touching it, solely through the effects of gravitational tides. At the opposite end of the spectrum are supermassive black holes, true cosmic titans found at the center of most known galaxies. These giants can have masses ranging from millions to billions of times the mass of the Sun, and their event horizons can extend over distances comparable to Earth's orbit or even farther. The central black hole of our galaxy, Sagittarius A star, is one such example, with about 4 million solar masses. These colossal objects likely play a fundamental role in the formation and evolution of galaxies, regulating the flow of matter and influencing the creation of new stars. Between these two extremes, we find intermediate mass black holes, a rare and still poorly understood type. Their masses can range from hundreds to thousands of times the mass of the Sun, and they are thought to form through the merger of several stellar black holes or the direct collapse of extremely dense star clusters. Detecting these objects is difficult, but recent evidence suggests they may exist at the heart of some globular clusters and dense star-forming regions. Beyond these, there is the intriguing hypothesis of primordial black holes, which would have formed in the first moments after the Big Bang. Unlike the others, their mass could vary drastically. Some would be tiny, smaller than an atom, but with masses equivalent to entire mountains. Others could rival stellar black holes. If they exist, some of these mini black holes may have completely evaporated over billions of years due to Hawking radiation, while others could still be wandering the universe, invisible and silent. The diversity of sizes and types shows that black holes are not all equal in terms of risk and impact. A stellar black hole passing near the solar system could cause significant disruptions, altering orbits and potentially ejecting planets from their paths. Our supermassive black hole, on the other hand, would rarely move through space at a speed sufficient to cross our path. But if it did, the consequences would be immeasurable. Even a primordial black hole, if sufficiently massive, could pose a localized threat, passing through our planet in seconds and leaving behind deep damage, even without swallowing it completely. Understanding the scale and nature of each type is crucial for us to imagine accurately what might happen in the scenario we are exploring here, a close encounter between Earth and one of these invisible giants. This analysis also helps us understand that in the vast theater of the universe, size is not a direct synonym for threat. Trajectory, speed, and the type of interaction with the environment are factors just as decisive as a black hole's mass. The event horizon is perhaps the most emblematic and intriguing feature of a black hole. It is not a physical surface, like the crust of a planet or the atmosphere of a star, but rather an invisible and absolute boundary that marks the point of no return. It is the imaginary line that separates the region of space where light can still escape from that, where gravity is so intense that not even radiation can break free. On the outside of this boundary, it is still possible to observe and measure the effects of the black hole. On the inside, everything that enters is doomed to an inevitable fate, the plunge toward the singularity. The position of the event horizon depends directly on the mass of the black hole. The more massive it is, the larger the radius of this boundary, known as the Schwarzschild radius. In a black hole with a mass equivalent to 10 suns, for example, the event horizon would be only a few dozen kilometers in diameter, a surprisingly small size compared to the scale of the universe, yet with gravitational power capable of capturing anything that crosses that limit. It is at this point that the escape velocity, the minimum speed required to break free from gravitational pull, reaches exactly the speed of light. For a distant observer, any object approaching the event horizon appears to slow down as it gets closer. The light emitted by the object stretches, shifting to longer wavelengths in a phenomenon called gravitational redshift. As a result, the object becomes darker and eventually disappears from our sight, appearing frozen at the edge, although in reality, for the object itself, the crossing occurs in a finite amount of time. This contrast between external perception and internal experience is one of the strangest and most counterintuitive consequences of general relativity. Once inside the event horizon, all possible trajectories, regardless of speed or direction, point toward the center of the black hole. It is as if space-time was so distorted that the natural path for everything is inevitably the fall toward the singularity. There is no stable orbit, no way to stop, and not even light, the fastest phenomenon in the universe, can defy this path. This is what makes the event horizon a definitive, impenetrable, and irreversible barrier. The event horizon is also the point where the mystery of physics deepens. On the outside, we can apply the known laws of gravity and electromagnetism to predict behaviors. On the inside, however, our theories stop offering clear answers. The singularity concentrates all the mass of the black hole in a point of infinite density, and describing this condition requires a unified theory that combines general relativity and quantum mechanics, something science has yet to fully develop. There is also a fascinating aspect. The event horizon is not a static barrier. It can grow if the black hole absorbs more matter and energy, or theoretically shrinks slowly over trillions of years due to Hawking radiation. This dynamism means that the horizon is, in a way, a living boundary, responding to the black hole's interactions with its surroundings. Understanding the event horizon is crucial to our hypothetical scenario, as it marks the point beyond which any approach would become fatal. In the case of a black hole passing close to Earth, even if our planet did not cross this boundary, its proximity alone could be enough to trigger devastating gravitational effects, altering orbits, tearing apart planetary structures, and destroying everything we know. At the heart of every black hole lies something so extreme that it defies logic, the known laws of physics, and even our imagination, the singularity. It is the central point toward which all matter and energy that cross the event horizon ultimately converge, compressed to infinite density within an infinitely small volume. It is a concept that, more than any other in astrophysics, reminds us that we still do not fully understand the universe. According to Einstein's theory of general relativity, when gravity overcomes all other forces, thermal pressure, electromagnetic repulsion, and even nuclear forces, matter can no longer resist. The collapse is total, continuous and absolute, until everything is crushed into a mathematically defined point, yet physically impossible to visualize. At this point, the curvature of space-time becomes infinite, and all equations describing the functioning of the cosmos cease to make sense. Based on our current knowledge, there is no way to predict what actually occurs within this region. What we do know is that the singularity represents the ultimate limit of gravitational collapse. It doesn't matter whether we are talking about a black hole with a few solar masses or a supermassive one with billions of solar masses. At the center, the fate is always the same. It is there that space and time, as we know them, cease to exist in recognizable forms. For anyone who were to hypothetically cross the event horizon, there would be no return. The trajectory would inevitably lead to this absolute concentration of mass and energy. Many physicists believe the singularity is the definitive proof that we need a theory uniting general relativity, which describes the universe on large scales, and quantum mechanics, which governs the world of subatomic particles. It is possible that once we achieve this theory, we will discover that the singularity is not exactly a point in the literal sense, but rather an extremely dense region where gravity and quantum effects interact in ways we cannot yet calculate. Some hypotheses even suggest that this region could somehow store information about everything that has fallen into the black hole, a concept connected to the famous information paradox proposed by Stephen Hawking. Another fascinating question is the nature of time within the singularity. For an external observer, anything falling into a black hole appears to take an infinite amount of time to reach the event horizon due to the effect of gravitational redshift. But for the one falling in, the journey to the singularity would occur in a finite amount of time, and once there, all directions in space would point toward the inevitable future, the center. This radical inversion of perspectives is one of the reasons black holes remain one of the greatest scientific enigmas. In the context of our scenario, imagining Earth being dragged into a black hole means envisioning the entire planet, its matter, energy, and even its history, compressed in a fraction of a second toward the singularity. No recognizable trace would remain, and all information about our existence would be forever trapped, inaccessible to the outside universe. The singularity, therefore, is not just the core of the black hole, it is the ultimate boundary of reality as we know it. And it is what gives meaning to the immense and silent threat these objects represent in the vast cosmic ocean. To fully understand the danger and fascination of a black hole, it is essential to grasp how it shapes and distorts the very fabric of reality, space-time. In the classical view of physics, space and time were separate entities, a fixed stage upon which matter moved. But the theory of general relativity, formulated by Albert Einstein, revealed that space and time are inseparable and form a single, flexible structure capable of being deformed by the presence of mass and energy. The greater the mass of an object, the greater the curvature it creates in the space-time around it. A black hole is in this sense the ultimate expression of this curvature. Its gravity is so intense that space-time is not merely slightly bent, as in the case of a planet or a star, but rather deformed to an extreme degree, creating a kind of deep, bottomless well. The secret behind the black hole's irresistible pull lies in this deformation. It's not that it pulls matter in the traditional sense, but rather that matter and light simply follow the natural path within this distorted space-time, a path that inevitably leads to the singularity. In regions close to the event horizon, the effects of this distortion become dramatic. Time, for example, no longer flows in the same way for all observers. To someone far from the black hole, the clock of someone approaching it will appear to slow down progressively, as if being stretched. This phenomenon, called gravitational time dilation, means that near a black hole, time passes more slowly compared to regions where gravity is weaker. In an extreme scenario, an astronaut spending just a few minutes near a massive black hole could return to find that, for the rest of the universe, centuries or even millennia had passed. This distortion affects not only time, but also space. Orbits around a black hole can behave anomalously, and the paths of particles and light are sharply bent, producing phenomena such as gravitational lensing. This effect, predicted by Einstein and confirmed by countless observations, causes the light from distant stars or galaxies to curve as it passes near a black hole, creating duplicate images, rings of light, or striking visual distortions. In the case of a black hole moving through space, this extreme space-time distortion moves with it, altering the geometry of space in a vast region around it. If one of these objects were to pass near the solar system, it wouldn't be just its direct gravity that affected the planets. The entire spatial architecture supporting their orbits would be subtly and then violently reshaped. Small changes in speed and trajectory would accumulate over time, and celestial bodies that once followed stable orbits could be flung out of the system or drawn into fatal paths. Distorted space-time also creates a disturbing phenomenon known as spaghettification, which occurs when the difference in gravity between two parts of an object, for example, an astronaut's head and feet, becomes so great that the body is stretched into an extremely thin strand before being torn apart. This is caused not only by gravitational pull, but also by the uneven curvature of space-time, which creates unbearable gravitational gradients. Thus, a black hole is not just a massive body exerting force on other objects, it is a sculptor of space and time itself. As we approach one, we are not merely moving through space, we are entering a radically different geometry from the one we inhabit, where distances, directions, and even the passage of time take on completely new meanings. Around a black hole, space is neither silent nor static. Although the black hole itself is invisible, its immediate surroundings can be among the most violent and energetically active places in the entire universe. This activity arises from the simple fact that, while nothing can escape from inside the event horizon, matter that is still outside can be heated, accelerated and torn apart in spectacular ways before crossing that point of no return. The first remarkable feature is the accretion disk. When gas, dust, or even entire stars approach a black hole, the relentless gravity pulls this matter into ever smaller orbits. The matter does not fall straight in. Instead, it forms a flattened disk, spinning at speeds close to that of light. Friction between particles and extreme compression heat this material to millions of degrees, emitting intense radiation across multiple frequencies, especially X-rays and gamma rays. It is through this radiation that we detect the presence of many black holes, since the black hole itself emits no light. Another impressive phenomenon is the formation of relativistic jets. In some cases, especially in supermassive black holes at the centers of galaxies, part of the material in the accretion disk is not immediately swallowed. Instead, it is channeled and expelled from regions near the event horizon, forming narrow beams of charged particles launched outward at speeds close to that of light. These jets can extend for thousands or even millions of light years, injecting colossal amounts of energy into interstellar space and influencing the birth and evolution of entire galaxies. In the vicinity of a black hole, we also find the gravitational frenzy of companion stars. In binary systems, a black hole can steal material from its neighboring star, forming a constant stream of gas spiraling into the accretion disk. This process can produce periodic bursts of radiation known as X-ray outbursts, which vary in intensity and frequency depending on the amount of matter being consumed. Another more subtle effect is the dragging of space-time, or the lens-thirring effect. A rotating black hole literally twists the space-time around it, causing any nearby object to be pulled in the direction of its rotation. This influences the shape and behavior of the accretion disk and even the trajectory of light particles, contributing to even more extreme visual and dynamic distortions. For a hypothetical observer approaching an active black hole, the scene would be both breathtaking and terrifying. A brilliant, incandescent disk spinning at inconceivable speeds, rays of light being distorted by gravitational lensing, and perhaps colossal jets being ejected into the depths of space. Yet the beauty of this view is inseparable from its absolute danger. The radiation emitted near a black hole can be lethal long before reaching the event horizon. Highly energetic X-rays and gamma rays can destroy biological molecules and sterilize any form of life over great distances. In the context of our scenario, a black hole passing close to Earth, these external effects would be the first visible and detectable signs of its presence. Long before we were physically drawn in, we could observe changes in cosmic radiation, see the night sky lit up by new and strange sources of light, and feel the impact of this radiation on the atmosphere. It is important to understand that the destructive power of a black hole is not limited to what happens inside its event horizon. Its influence extends over vast distances, and the violence it unleashes on nearby matter can completely transform entire regions of space. If one of these cosmic monsters crossed our planet's path, we wouldn't need to be swallowed to suffer severe consequences. The mere proximity of its presence could change Earth's fate forever. Imagine that in a distant point of the galaxy, a wandering black hole, silent, invisible, and without any companion star, moves along a trajectory that, by chance, crosses the path of our solar system. This type of object, without matter to form an accretion disk, would not emit intense radiation that could easily give it away. Its presence would only reveal itself through subtle gravitational effects, initially imperceptible to the human eye, but detectable by extremely sensitive instruments. The first sign of this approach would likely come from anomalous deviations in the orbits of distant bodies, such as those inhabiting the Oort cloud, an immense sphere of comets surrounding the solar system at distances up to 100,000 times the separation between Earth and the Sun. Small changes in the trajectory of these comets, measured over months or years, could indicate the influence of a massive yet unidentified object. Astronomers would detect these anomalies and, upon recalculating the data, realize that something invisible and extremely dense was approaching. As the black hole advanced, its gravitational field would begin to interact more intensely with the solar system. Outer planets such as Neptune and Uranus could show subtle changes in their orbits, and space probes in distant regions would record deviations from their planned trajectories. This would be the second stage of detection, the confirmation that we are not dealing with an unknown planet or a gigantic frozen body, but rather with an object whose mass is so concentrated that it could only be a black hole. As it drew even closer, the gravitational influence would become impossible to ignore. Asteroids from the Kuiper Belt region could be deflected and begin crossing into the inner solar system, increasing the risk of collisions with planets, including Earth. The Sun, although far more massive, would also feel the presence of this visitor, and its gravitational interactions could slightly alter its position relative to the solar system's center of mass. These changes, however small, would affect the orbital balance of all planets. In a more dramatic scenario, depending on the trajectory and speed of the black hole, we could see visible effects in the sky even before its closest approach. If there were any remnants of gas or interstellar dust in its path, this material would be accelerated and heated, emitting detectable radiation. Satellites and telescopes would capture increasingly clear signals. The invisible monster was coming. The moment of greatest risk would occur during its passage through the interior of the solar system. If the black hole was small, but passed very close, it could directly capture some celestial bodies, ripping moons from their orbits, and possibly pulling smaller planets into unstable paths. If it were farther away but more massive, its effects might be subtler but equally dangerous. Permanently altered orbits, planets ejected into interstellar space, or comets sent on collision courses. In this scenario, Earth would not need to fall into the event horizon to face a tragic fate. A significant orbital disturbance would be enough to send the planet too far from the Sun, plunging it into an eternal ice age, or too close, subjecting it to unbearable heat. And even if we remained in the same orbit, the passage could bring intense radiation, particle storms, and catastrophic impacts from deflected objects. This hypothetical encounter reminds us of something fundamental. The universe is neither static nor safe. It is an ocean in constant motion, where colossal masses travel silently across unimaginable distances, and Earth, despite all its history and life, is nothing more than a small vulnerable point in this cosmic sea. The first gravitational impact of a black hole approaching the solar system would not be an immediate dramatic spectacle, but rather a series of almost imperceptible alterations that accumulate over time until they become devastating. Unlike an asteroid, whose threat can be visualized through telescopes, a wandering black hole acts silently, modifying the gravitational dance of all celestial bodies long before it is detected by the human eye. As its colossal mass warps the surrounding space-time, It would begin to exert influence over the most distant objects in the solar system. The Oort cloud, with its trillions of comets, would be the first to feel the presence of this invisible visitor. A slight gravitational displacement could be enough to launch thousands of these icy bodies into unstable trajectories. Some would be expelled into interstellar space, but many would be redirected toward the Sun, and consequently toward the inner regions where Earth orbits. As the black hole drew closer, its gravitational pull would combine with that of the Sun, creating a distorted field that would alter the orbits of planets and asteroids. Outer planets such as Neptune, Uranus, and Saturn could be gently pulled into new trajectories, modifying the orbital resonance that has kept the solar system balanced for billions of years. These changes, even if small, could trigger a cascade effect, disrupting the stability of the orbits of the inner planets, including that of Earth. This imbalance would also manifest in the trajectory of asteroids in the main belt, located between Mars and Jupiter. Small changes in speed and direction could turn some of them into direct threats, placing them on collision courses with Earth or other planets. This would mean a drastic increase in the risk of impacts capable of causing mass extinctions and global climate changes. A particularly dangerous aspect of this initial gravitational impact is that it would occur gradually, and most of the world's population would not even realize what was happening. Only astronomical observatories and planetary monitoring networks would be able to detect the deviations, and even then, at first they might mistake these signals for natural fluctuations or measurement errors. By the time the threat was confirmed, the black hole would already be much closer, and the effects would be impossible to reverse. Furthermore, this gravitational distortion could produce subtle yet dangerous consequences for Earth itself, even before any drastic orbital changes occurred. The additional pull could cause variations in ocean tides, alter the planet's internal dynamics, and, in extreme cases, influence tectonic and volcanic activity. Although these effects would be small compared to what would happen in an extreme approach, they would be clear signs that something colossal was interfering with the natural balance we know. This initial moment of gravitational interaction is like the first touch of an approaching giant wave, silent and almost imperceptible, yet carrying the promise of an inevitable impact. It is the prelude to transformations that, once triggered, completely escape human control and remind us that, on the cosmic chessboard, Earth is nothing more than a fragile piece at the mercy of immeasurable forces. When we think about the dangers of a black hole approaching the solar system, it is natural to first imagine the direct consequences for Earth. However, even before our planet feels the full impact of this cosmic force, the Sun, the gravitational anchor that keeps all the planets in their orbits, would be affected, and any change in the Sun's balance would inevitably be reflected in the entire architecture of the solar system. The Sun is a massive star containing more than 99% of the total mass of the solar system, and its gravity dominates every planet, moon, asteroid, and comet. But the gravity of a nearby black hole could compete with this force. Depending on the distance and mass of the intruder, the Sun's position relative to the solar system's center of mass could be displaced. This displacement, even if minimal, could break the resonances and alignments that have maintained orbital stability for billions of years. If the black hole was sufficiently massive and approached within a critical distance, it could even capture the Sun into an unstable orbital motion, altering the way our star moves through the galaxy. This, by itself, would already trigger radical changes in the trajectories of the planets. But there is an even more dramatic scenario. If the black hole came at high speed and passed extremely close, it could literally tear the Sun from its current position, ejecting it far from its original solar system, or, in the worst case, capturing it into a deadly orbit around itself. Another possible effect is related to the matter the Sun could lose. Although it is extremely stable, the star is composed mostly of plasma, a material that, under intense gravitational influence, could be slowly pulled away. This process, called stellar accretion, could form a stream of matter flowing toward the black hole, creating a lethal link between our star and the intruder. The result would be not only the gradual loss of the Sun's mass, but also changes in the pressure and internal balance that sustain it, affecting its activity cycle and radiation output. Even without mass loss, the approach of a black hole could affect the Sun's magnetic behavior. The solar magnetic field is sensitive to variations in rotation, and to changes in the distribution of internal mass. Small disturbances could intensify or reduce sunspot activity, alter the cycle of flares and coronal mass ejections, and consequently affect the space weather that reaches Earth. These changes, though indirect, would have a direct impact on our atmosphere, communications, and even the global power grid. If the influence were extreme, the Sun could even change its trajectory in the Milky Way, dragging along all planets still gravitationally bound to it. This would completely transform our relationship with the rest of the galaxy, taking us to regions with different star densities and radiation fields. And, in an even more catastrophic approach, the Sun could be swallowed by the black hole, an event that would release a colossal amount of energy, visible from billions of light years away, but which would mean the immediate end of our planetary system. In any of these scenarios, what becomes clear is that the presence of a black hole in the Sun's neighborhood is far more than a threat to Earth. It is a force capable of completely reshaping the structure of the solar system, destroying balances that took billions of years to form, and bringing an end to the era of stability that allowed life to exist. If a black hole approached close enough to directly influence Earth, the impact on our gravitational field would be profound and immediate. Gravity, which normally maintains a stable relationship between our planet, the Moon, and the Sun, would also begin responding to the presence of a new colossal force. This imbalance could initiate a chain of consequences, affecting everything from Earth's rotation to the stability of its orbit. The first noticeable effect would be the alteration of gravitational tides. Currently, these tides are caused mainly by the Moon and, to a lesser extent, the Sun. But a nearby black hole, even millions of kilometers away, could generate gravitational differences so intense that the oceans would behave in completely anomalous ways. Instead of regular cycles of high and low tides, we could see extreme oscillations, with giant waves in some regions and drastic retreats in others. This redistribution of water would affect coastal ecosystems, shipping routes, and even the habitability of coastal cities. Earth's gravitational field also acts on its own internal structure. An external force of such magnitude could intensify tectonic stress, causing a sudden increase in seismic and volcanic activity. Regions prone to earthquakes could experience much more frequent and intense events, while active and dormant volcanoes could erupt due to the redistribution of pressures in the Earth's mantle. Additionally, the uneven gravitational interaction, stronger on one side of the planet than on the other, could generate a phenomenon similar to spaghettification, but on a planetary scale. Although Earth would not be stretched like a small object, differences in attraction in distinct regions could cause temporary deformations in the crust and even slightly alter the planet's shape. These deformations, combined with oscillations in rotation, could influence global climate and wind patterns. The gravitational bond between Earth and the Moon would also be affected. Our Moon could have its orbit disturbed, becoming more eccentric, or even being torn away from Earth's influence, which would have drastic effects on climate stability and the balance of the planet's rotational axis. Without the Moon to stabilize our axial tilt, the seasons could become chaotic, with abrupt and unpredictable temperature shifts. In an extreme scenario, Earth's own orbit around the Sun could be altered. If the black hole's approach occurred at a specific angle and speed, we could be pulled into a more distant or a closer trajectory to the Sun. In the first case, we would enter a permanent global winter. In the second, we would face overheating that could evaporate the oceans and wipe out most life. The most alarming aspect is that many of these effects would not be instantaneous. Some changes could take weeks or months to manifest, creating a false initial sense of security. But once underway, the chain of events would be irreversible, and Earth would live under a new gravitational balance, or, in the worst case, under the complete absence of any stable balance. These changes show that the danger of a nearby black hole is not just in being swallowed by it, but also in its ability to dismantle the delicate system of forces that keeps our planet habitable. When we think of a black hole, the first image that comes to mind is that of a relentless gravitational well, capable of devouring everything that approaches. But the danger is not limited to gravity. Even without touching the event horizon, a black hole can pose a lethal threat through something invisible, and much faster than any gravitational disturbance: high-energy radiation. This radiation does not come from the interior of the black hole, since nothing can escape from there, but rather from the regions around it, where infalling matter is accelerated and heated to extreme temperatures. If the black hole were passing through a region rich in gas, dust, or small celestial bodies, these materials would be drawn in and would form an accretion disk. In this disk, intense friction and compression would cause the matter to emit colossal amounts of electromagnetic radiation. Among these emissions, the most dangerous to life would be X-rays and gamma rays, forms of ionizing radiation capable of penetrating biological tissues and destroying essential molecules, including DNA. Earth, partially shielded by the atmosphere and magnetosphere, is not defenseless against ordinary cosmic radiation. However, the intensity of emissions from an active black hole could far exceed the planet's natural protective capacity. High-energy X-rays could ionize the upper layers of the atmosphere, damaging the ozone layer and allowing lethal ultraviolet radiation from the sun to reach the surface. At the same time, gamma radiation could penetrate more deeply, affecting entire food chains by destroying photosynthetic microorganisms in the ocean, the base of almost all marine life. Another danger comes from relativistic particles expelled in polar jets by some black holes, especially supermassive ones. These jets, composed of electrons and protons accelerated to speeds close to that of light, could hit Earth with enough energy to cause satellite failures, damage power grids, and even induce genetic mutations in living organisms. Although these jets are highly directional, it would only take Earth being in their path for the effects to be immediate and catastrophic. Even an inactive black hole not currently feeding an accretion disk can pose a risk if its passage through the solar system sets large amounts of matter in motion. Deflected asteroids and comets could collide with planets, releasing energy equivalent to millions of nuclear bombs, lifting enough dust to block sunlight, and plunging Earth into a prolonged winter. While not radiation in the strict sense, this indirect effect results from the same force, the extreme interaction between gravity and matter. One of the most concerning aspects of this invisible threat is that it may precede the physical arrival of the black hole. Radiation travels at the speed of light, meaning that as soon as an accretion disk or relativistic jets form, lethal energy will begin to reach Earth almost instantly. And unlike gravity, which affects everyone equally, radiation can have localized and differentiated effects depending on intensity, particle type, and the point of impact on Earth's surface. Thus, even if Earth managed to avoid gravitational capture or a direct collision with a black hole, mere proximity to one of these active objects could be enough to trigger a global environmental collapse. It is a grim reminder that in the universe, the most dangerous forces are often those we cannot see with the naked eye, and that by the time we finally perceive them, it may be too late to escape. The approach of a black hole to the solar system would not only alter the invisible physics of space-time or the gravity we feel on Earth, it would also leave a visible and irreversible mark on the very sky we know. The celestial dome, with its familiar constellations and patterns that have accompanied us for millennia, would be slowly distorted until it became unrecognizable. Each night, a careful observer would notice that something was wrong, even without being able to explain what. The first visual clue would be gravitational lensing. The presence of a black hole distorts space-time, bending the path of light that passes around it. This would make stars and galaxies in the background appear displaced, duplicated, or stretched into luminous arcs. For someone observing without instruments, these changes might be subtle at first, but over time they would become obvious, especially if the black hole were relatively close and crossing the field of view of well-known constellations. If the black hole were accumulating matter in an accretion disk, the transformation would be even more dramatic. In the emptiness of space, an unusual bright spot would appear, emitting intense light at various frequencies, with a glow that could outshine any star in the night sky. To the naked eye, it might look like a fixed bright point, but through telescopes, it would reveal a spectacle of rotation, radiation, and visual distortion. The sky would also change due to indirect effects. The arrival of comets and asteroids deflected by the black hole's gravity would create meteor showers far more intense and frequent than those we know today. Some nights could be lit by dozens or even hundreds of streaks of light crossing the sky, the result of fragments entering the atmosphere. Although visually beautiful, these events would be clear signs of instability and imminent danger. As the approach continued, the most striking visual change could occur if Earth began to experience significant changes in its orbit or tilt. Small variations could shift the alignment of constellations, making them rise and set in different positions than usual. More extreme changes could even alter the very length of day and night, creating strange, disorienting skies where familiar stars no longer occupy the same places, and where the moon could move farther away or come unusually close. If we were close enough for radiation ejected by the black hole to directly hit the atmosphere, we could witness unusual luminous phenomena, such as giant auroras, visible far beyond the polar regions. These curtains of light, caused by the interaction of radiation with atmospheric particles, could tint the sky with intense colors, ranging from deep red to bright green and violet. Though breathtaking, they would be a chilling reminder of the invisible energy striking us. In the final stage of approach, the sun itself could appear different. Sunlight, as it passed through the region of space-time, distorted by the black hole's presence, could undergo subtle changes in color and intensity. If the alignment were perfect, we might even witness a solar gravitational lensing event, creating a ring of light around the intruder, a phenomenon as rare as it is brief, but one that would forever mark humanity's perception of the sky. And even if somehow Earth survived the passage of this cosmic visitor, the sky would never again be the same. The altered orbits, deflected objects, and new arrangement of the stars would remain as permanent scars of an encounter that would forever change our vision of the universe. One of the most dangerous scenarios during the passage of a black hole through the solar system is the possibility of orbital collapses, situations in which planets, moons, and other celestial bodies lose the stability of their trajectories and end up being expelled into interstellar space or captured in fatal spirals toward the black hole itself. The orbital harmony we know today is the result of billions of years of balance between the sun's gravity and the motion of the planets. Just one sufficiently strong disturbance could cause this entire architecture to collapse. The risk begins with the most distant planets, such as Neptune, Uranus, and Saturn. Being farther from the sun, the gravitational force that keeps them in their orbits is weaker, which makes them more susceptible to the influence of a colossal mass approaching. A black hole passing relatively close could alter their trajectories in subtle but sufficient ways, so that over time, these deviations would amplify, leading to increasingly unstable orbits. In extreme cases, a giant planet could be torn from the solar system and launched into the interstellar void as a rogue planet. These alterations would not be limited to the outer planets. Any change in the orbit of a gas giant like Jupiter would have profound effects on the inner planets, including Earth. Jupiter acts as a gravitational shield, diverting or capturing many comets and asteroids that could strike our planet. If the orbit of this giant were displaced, the asteroid belt and the paths of countless smaller bodies would be completely reorganized, exponentially increasing the risk of catastrophic impacts. The moon could also fall victim to an orbital collapse. If Earth's orbit were altered, even slightly, the gravitational balance that keeps the moon around us could break. In that case, it could be captured by the black hole, crash back into Earth in a devastating collision, or escape into space as a wandering body. Any of these possibilities would have fatal consequences for life on the planet, as the moon stabilizes the tilt of our axis and directly influences climate and tides. Beyond planets and moons, countless asteroids and comets would have their trajectories altered. A black hole crossing the solar system could transform relatively stable regions, such as the Oort cloud and the Kuiper belt, into constant sources of lethal projectiles. These bodies, redirected toward the inner space, could trigger an era of intense bombardment, similar to what occurred in Earth's early days, but on a potentially much more destructive scale. The most extreme scenario of orbital collapse would be one in which Earth itself is directly affected. If the black hole's gravitational influence were strong enough, our planet could be torn from its current orbit. Two fates would be possible: being launched into interstellar space, becoming a frozen, sunless planet, or being slowly pulled into a death spiral toward the black hole. In the first case, life would have only a short time to survive. In the second, there would be no chance of escaping the final fate. Orbital collapses are a reminder that in the cosmos, stability is only a temporary condition. Our solar system is like a mechanism of perfectly tuned gears, but extremely sensitive to external disturbances. A black hole passing nearby would not even need to touch us to turn that harmony into irreversible chaos. The approach of a black hole would not only affect the orbital mechanics of the solar system, it could also drastically and irreversibly reshape Earth's atmosphere and climate. Our atmosphere is a delicate system, maintained in balance by factors such as solar radiation, the planet's rotation, gravity, and interactions with the ocean. Any significant disturbance to this set of conditions could trigger rapid and extreme transformations, capable of making the planet uninhabitable in a short time. The first impact could come from changes in Earth's orbit. A small alteration in the average distance between Earth and the Sun would already be enough to modify the amount of energy received. If the black hole pulled us slightly closer, solar radiation would increase, raising global temperatures and causing the accelerated evaporation of the oceans. This would lead to a runaway greenhouse effect, similar to what occurs on Venus, with scorching temperatures and a dense, toxic atmosphere. On the other hand, if the orbit moved us farther away, we would enter a permanent ice age, with the freezing of seas and continents, and the loss of most life. Even without a drastic change in orbit, the gravitational influence of a black hole could alter Earth's axial tilt. Currently, our axis is tilted at approximately 23.5 degrees, which determines the seasons of the year. A sudden change in this tilt could lead to climate extremes. Regions once temperate could turn into scorching deserts, while tropical areas could freeze. Irregular and unpredictable seasons would cause the collapse of ecosystems and entire food chains. In addition, the radiation associated with an active black hole, mainly X-rays and gamma rays, could interact with the upper atmosphere, destroying part of the ozone layer. This would allow more ultraviolet radiation from the sun to reach the surface, increasing the risk of skin cancer, harming photosynthesis, and upsetting terrestrial and marine ecosystems. In extreme cases, this radiation could ionize large layers of the atmosphere, altering weather patterns and generating much more intense electrical storms. Another serious consequence could come from changes in ocean tides. An increase in external gravitational force would deform the shape of the oceans, modifying ocean currents that are fundamental to climate regulation. The Gulf Stream, for example, responsible for keeping Western Europe's climate relatively mild, could be disrupted, triggering abrupt cooling in some regions and extreme heating in others. Finally, the accumulation of meteor and comet impacts diverted by the black hole's gravity would add another catastrophic factor. Collisions of this kind would raise immense clouds of dust and soot, blocking sunlight for months or years, a phenomenon known as impact winter. Even if temporary, it could be enough to destroy crops, lead to global famine, and cause a civilizational collapse. In any scenario, the effects on Earth's atmosphere and climate would be devastating, and the planet's habitability could be lost in a surprisingly short time. The approach of a black hole, even without swallowing our planet, would have the power to transform the sky, the land, and the sea into elements of an unrecognizable world. Among all the possible scenarios involving the approach of a black hole, the direct gravitational capture of Earth is without a doubt the most extreme and most fatal. Unlike disturbances that would slowly alter our orbit or change the climate, being captured would mean entering an inevitable path toward the event horizon, a road with no possibility of return, where every second would bring us closer to total collapse. Capture could occur in two main ways. The first would be orbital capture, in which Earth, passing near the black hole, would lose enough energy to be pulled in and forced to orbit it. At first, this might seem like a stable situation, like the Moon around Earth, but in practice it would only be an intermediate step toward destruction. With each revolution, tidal forces would drain energy from the orbit, causing the planet to spiral closer and closer until it crossed the event horizon. During this process, tidal effects would be so intense that the surface would fragment, oceans would rise into waves thousands of meters high, and Earth's crust would break into incandescent slabs. The second possibility is even more dramatic, a direct plunge. In this case, Earth's trajectory, strongly influenced by the black hole's gravity, would lead it without deviation into a fatal dive. In this scenario, there would be no orbit, only constant acceleration. In a matter of days or even hours, depending on the initial distance, we would cross space until we reached regions where light can no longer escape. To an outside observer, Earth would appear to slow down and freeze in time as it approached the event horizon. its glow becoming increasingly red and faint until it vanished completely. But for those on the planet, the fall would be felt as a continuous and crushing increase in gravity, accompanied by increasingly violent deformations on the surface. Spaghettification would be inevitable. The term, as curious as it may sound, describes an extremely real phenomenon. The difference in gravity between the part of the planet closest to the black hole and the farthest part would be so extreme that the entire planet would begin to stretch in the direction of the fall and compress in the other directions. Geological structures would shatter, seas would rise into colossal columns, and the atmosphere would be torn away in fragments. No form of life could survive this physical stress. Even before crossing the event horizon, radiation emitted by the accretion disk around the black hole, if it were active, would already have sterilized the surface. Crossing the horizon would not be felt as a physical barrier, but from that point onward, not even the information that we still exist could escape into the universe. All the contents of our history, culture, and life would vanish forever into the darkness. This final scenario, as distant and unlikely as it may be in astronomical terms, is a reminder that the universe guarantees eternity to no world. The capture of a planet by a black hole is the most definitive form of disappearance. It leaves no ruins, no traces, only an absolute silence where once there was a home. The term spaghettification may sound almost comical at first glance, but it describes one of the most extreme and lethal physical processes in the universe. It is the inevitable fate of any object, whether a spacecraft, an entire planet, or even a star, that ventures too close to a black hole, crossing what is called the critical tidal distance. From that point onward, the difference in gravitational intensity between the nearest and farthest parts of the object becomes so colossal that its structure can no longer resist, being stretched and deformed until it reaches absurdly thin and elongated shapes like strands or ribbons of matter. In the case of a hypothetical human falling toward a black hole, the effect would be brutal. The tidal force would act with much greater intensity on the feet than on the head, stretching the body along one axis and compressing it along the other two. This difference would not be a matter of a few kilograms or tons, but forces so intense that they would overwhelmingly exceed the resistance of any molecule or atomic structure. In fractions of a second, the body would be reduced to a stream of particles, still following the inevitable path toward the singularity. When the falling object is something much larger, such as Earth, the spaghettification effect occurs on a planetary scale. First, the oceans would be drawn into immense columns of water, stretching toward the black hole. The Earth's crust would begin to rupture into large fissures, spewing magma and releasing immeasurable seismic energy. Entire mountains would rise and collapse within minutes, while the atmosphere would be stripped away into space. At the same time, on the side opposite the black hole, gravity would be weaker, creating an even more extreme contrast and accelerating the planet's disintegration. The intensity of this phenomenon depends on the type of black hole. In stellar mass black holes with only a few dozen solar masses, the fatal tidal zone lies outside the event horizon, meaning spaghettification would occur even before crossing the point of no return. In supermassive black holes, with millions or billions of solar masses, the event horizon is so large that the difference in gravity within it is smaller at first, and spaghettification would only occur closer to the singularity, but regardless, it would still be inevitable. From the standpoint of physics, this process is a direct consequence of the extreme curvature of space-time. A black hole's gravitational field does not act uniformly. It is more intense the closer one is to the source. This variation, known as the gravitational gradient, is what generates the tidal force responsible for destroying any structure. There is no material, technology, or form of life capable of withstanding it. Spaghettification, therefore, is not just a dramatic metaphor. It is the final physical stage before total disappearance inside a black hole. After it, there are no organized particles, memories, or structures left that we can recognize. Everything that once existed becomes part of the inevitable flow toward the singularity, where matter ceases to have meaning as we understand it. It is a silent and absolute end, with no explosion or sound, only the final deformation, followed by the plunge into total darkness. In the universe, few images are as powerful and terrifying as that of an entire world being stretched to its limit, then disappearing without leaving a trace. In a scenario where a black hole approaches the solar system, humanity's first instinctive reaction would be to look for a way to escape. But when the issue is analyzed based on current physics and engineering, it quickly becomes clear that the idea of fleeing from such an event is, in practice, impossible. The scale of energy and the time frames involved exceed by many orders of magnitude any technological capability we possess, and perhaps even any capability we might achieve in centuries. The most obvious escape would be to change Earth's orbit, to move it away from the fatal trajectory. This would require applying a constant force over an extended period, shifting billions of trillions of tons of planetary mass. Even if we used all available energy resources on the planet, including nuclear and solar energy, we would not come close to generating the necessary effect before the black hole was near enough to render any effort useless. Another alternative would be to abandon Earth and attempt to evacuate humanity to another star system. This plan, which at first glance seems more plausible, faces even greater obstacles. To escape the combined gravitational influence of the Sun and the black hole, we would need spacecraft capable of traveling at speeds close to that of light. The propulsion technologies we currently master, chemical, nuclear, or electric, are far too slow for this purpose. Even the most advanced theoretical propulsion concepts, such as laser sails or fusion engines, would require centuries or millennia to carry a human colony to a nearby habitable planet. Time would also be an unforgiving enemy. Detecting a rogue black hole early enough to plan any significant action would require a global monitoring network with reach far beyond what we have today. If its approach were detected only a few years or decades before the gravitational impact, any large-scale escape plan would be unfeasible. Evacuating billions of people in such a short time is far beyond our logistical capabilities. Even assuming we had somewhere to go, some might imagine more creative or desperate solutions, such as using the black hole's own gravity to slingshot ships away, a concept inspired by the gravitational assist maneuvers we already use with space probes. While theoretically possible, this idea is extremely risky. Any miscalculation would send the ship directly toward the event horizon. In addition, the radiation and tidal forces near the black hole would make navigation nearly impossible. There is also the purely theoretical hypothesis of using wormholes or shortcuts in space-time to escape, if they exist, and we could manipulate them. However, this is a solution that, for now, belongs more to science fiction than to applied science. There is no practical evidence that we can create or stabilize a wormhole, much less control it to evacuate an entire planet. In the end, the uncomfortable truth is that, faced with a close encounter with a black hole, there is no possible escape one. With current knowledge and technologies, our only real defense lies in distance, that is, in the hope that such events occur only on astronomical timescales far beyond the lifespan of human civilization. The approach of a black hole is one of the rare cosmic threats against which neither advanced planning nor technological power would be enough to ensure survival. It is a reminder that, in the universe, there are forces that surpass any capacity for reaction, and that our continued existence depends not only on our ingenuity, but also on a considerable measure of cosmic luck. In a scenario where a black hole approaches the solar system, the difference between being caught by surprise or having even the slightest chance to prepare would depend entirely on science and humanity's ability to detect and monitor cosmic threats. Unlike phenomena such as asteroids or comets, which can be visually detected with relative ease, a wandering black hole is invisible to light. It can only be identified by its gravitational effects on what surrounds it, or if it is active, by the radiation emitted by infalling matter. This makes astronomical surveillance not just desirable, but vital. The first line of defense would be precision astronomy. Ground and space-based observatories already monitor small variations in the positions and movements of stars. Techniques such as astrometry make it possible to detect the wobble of stars caused by the passage of an invisible massive object. If a black hole was several light-years away and moving toward us, it would be possible to notice anomalies in the trajectories of background stars or in distant bodies of the solar system, such as those in the Oort cloud. Another essential tool is high-energy radiation detection. If the black hole were capturing matter, even in small amounts, space telescopes specialized in X-rays and gamma rays such as the Chandra X-ray Observatory or the Fermi Gamma-ray Space Telescope, could detect its signature. This radiation, though dangerous, also acts as a beacon revealing the intruder's presence. Furthermore, advances in the gravitational wave astronomy have opened a new possibility for detection. Observatories such as LIGO and Virgo are already capable of detecting ripples in spacetime caused by massive events, like the merging of black holes. Although a lone traveling black hole would not produce intense gravitational waves if it interacted with another massive body along its path, we could receive that signal as an early alert to its location and movement. International coordination would be crucial. A global monitoring network, combining data from different observatories, would allow any suspicious detection to be quickly confirmed and its trajectory precisely calculated. Institutions such as the International Astronomical Union and space agencies like NASA, ESA, and CNSA would need to work together, sharing information without delay. The sooner we learned of the threat, the more time we would have to study its likely effects and plan responses, even if those responses were merely measures to mitigate the impact on Earth. Science would also play a key role in preparing the population for the event. This means translating technical data into clear information, avoiding both panic and underestimation of the risk. Computer models could realistically simulate possible interactions between the black hole and the solar system, predicting which planets, moons, and regions would be most affected. However, even with all this capability, there is a physical limit to what we can do. Detecting a black hole decades in advance would only be possible if it were emitting some form of radiation or if its gravitational effects were perceptible long before the critical approach. If we were dealing with a fast, small, and silent intruder, detection could occur too late for any significant action. Ultimately, the role of science in the face of such a disaster would not be to prevent the inevitable, but to understand, document, and, as much as possible, reduce the damage. Even if destruction could not be avoided, we would still have the opportunity to record the event in unprecedented detail, an observational farewell that, paradoxically, would increase our knowledge of the cosmos. Detecting a wandering black hole in time to react would require an early warning system far more advanced than anything we have today. The stealthy nature of these objects, invisible in visible light and perceptible only through gravitational effects or high-energy radiation, makes the task extremely difficult. However, technological advances in recent decades point to a future in which, at least theoretically, we could identify the approach of one of these cosmic giants with enough lead time to take mitigation measures or carry out limited evacuation. The first pillar of this defense would be a global network of optical and infrared telescopes, capable of continuously monitoring the entire sky, detecting even the slightest shifts in the positions of stars and distant planets. Platforms like the Vera C. Rubin Observatory are already approaching this capability, with ultra-sensitive cameras able to register minimal variations in brightness and position. Infrared is particularly useful, as a black hole capturing matter will heat the surrounding material, emitting radiation detectable in this spectrum. The second pillar would be space telescopes dedicated exclusively to the detection of X-rays and gamma rays, such as Chandra and Fermi, but operating as a network to cover the entire sky in real time. An active black hole, even a faint one, will produce high-energy signatures when interacting with any amount of matter. Detecting this early signal could give us years of advantage before its arrival in the solar system. The third indispensable element would be gravitational wave detectors. Although a solitary black hole does not generate large-scale detectable waves, its interaction with other massive bodies or stellar systems could produce subtle signals. Networks such as LIGO, Virgo, and the future LISA, Laser Interferometer Space Antenna, will expand our sensitivity to these ripples in spacetime, enabling the location and tracking of invisible objects billions of kilometers away. To complement these technologies, we could deploy two autonomous interstellar probes, distributed around the outskirts of the solar system. Equipped with gravitational sensors and high-sensitivity cameras, these probes would form an early detection barrier, reporting any anomaly before it reaches inner regions. This concept resembles an expanded planetary defense system, but on an interplanetary scale. Beyond detection technology, it would be essential to develop artificial intelligence algorithms capable of analyzing trillions of data points in real time, filtering out false alarms and identifying characteristic patterns of an approaching black hole. Reaction time is critical, while detection 50 or 100 years in advance could allow for adaptation strategies or limited escape. Discovering the threat only a few years before would mean a scenario with virtually no practical options. Finally, the usefulness of these technologies would depend on international cooperation. Data from observatories around the planet would need to be shared without restrictions, and decisions on how to communicate with the population would have to be swift and transparent. An early warning system would not only serve to try to save lives, but also to coordinate scientific efforts, documenting the event in as much detail as possible before the worst occurs. Ultimately, investing in early warning technologies against threats such as black holes is not just a matter of remote survival. It is also a way to deepen our knowledge of the cosmos and to be prepared to deal with rare events that have absolute consequences. If science confirmed that a black hole was approaching and that its effects on Earth would be inevitable, humanity would enter a stage of mobilization without precedent. It would be a challenge not only technological, but also social, political, and ethical, requiring rapid decisions in a scenario of limited resources and insufficient time. Attempts at salvation would depend entirely on the interval between detection and the final impact. The most obvious plan, often depicted in science fiction, would be flight to another world. This could mean sending a fleet of ships to colonize nearby exoplanets, such as those orbiting stars in our galactic neighborhood, for example, Proxima Centauri. However, even the nearest star system is more than 4 light-years away, and with current technology it would take tens of thousands of years to get there. Nuclear fusion propulsion or systems based on laser sails could reduce this time to decades, but we are still far from making such technologies viable on a large scale, and even further from being able to transport millions or billions of people. Another theoretical possibility would be moving Earth to a new safe orbit. This would involve colossal gravitational pushes using massive asteroids or planetary engines, gigantic structures capable of applying continuous force to the planet over centuries. Although this idea is studied in the field of planetary engineering, it would require resources and time that we simply would not have if the black hole were only a few decades away. A more pragmatic, though limited scenario would be the creation of long-term underground or submarine shelters to preserve a fraction of the population during the worst effects. However, this measure would only make sense in cases where Earth remained habitable after the black hole's passage, which would be unlikely if we faced a close and direct approach. Even so, some governments might invest in preserving libraries of knowledge, seed banks, DNA, and essential technologies, aiming to rebuild civilization in the future if there were a chance. There would also be discussion of building ark ships, self-sustaining spacecraft designed for extremely long interstellar journeys. These arks would function as closed habitats, capable of sustaining generations of humans for millennia as they traveled toward potentially habitable destinations. While conceptually possible, such projects would require precision engineering, enormous amounts of resources, and global cooperation, something that, in practice, could be undermined by political and economic disputes. Another approach, almost desperate in nature, would be trying to interact with the black hole itself, to use its gravity as a slingshot to propel ships at unprecedented speeds. This maneuver, while plausible in theory, would involve almost absolute risks. Any miscalculation would send the ship directly into the event horizon, and, as much as it sounds like fiction, bolder ideas would inevitably arise, such as trying to create artificial wormholes, or manipulating space-time with negative energy to open instantaneous escape routes. However, all of these solutions remain purely hypothetical and without any known practical application. The harsh reality is that even with all efforts, saving all of humanity would be impossible. The attempts would focus on preserving a small number of people and the greatest possible volume of knowledge, art, and history, so that if, in some distant future, a safe place remained, something of our existence could begin anew. The encounter with a black hole is not only a physical challenge, it is also a test of how our species faces the inevitability of finitude. Over the past few decades, science fiction has been one of the main laboratories of ideas for exploring what could happen if humanity were to face a black hole. Writers, filmmakers, and screenwriters have turned this phenomenon into a symbol of mystery, destruction, and sometimes even hope. Although many of these portrayals deviate from the actual laws of physics, they play an important role, sparking public interest and prompting reflections on our place in the cosmos. A striking example is the film Interstellar, 2014, which brought to the general public one of the most realistic depictions ever made of a black hole, the fictional Gargantua. With scientific consulting from physicist Kip Thorne, Nobel Prize winner, the film impressively showed effects such as gravitational lensing and extreme time dilation. In the plot, proximity to Gargantua causes a few hours on the surface of a nearby planet to correspond to decades for those who remain far away. This idea is scientifically sound and derives directly from the theory of general relativity. In contrast, other films and series use black holes as instant portals to other universes or dimensions, as in Stargate or certain episodes of Star Trek. Although black holes could theoretically be connected to space-time solutions known as wormholes, there is no evidence that they could be used in practice as safe shortcuts. These approaches are more narrative than scientific, but they encourage discussions on concepts such as parallel universes and interstellar travel. Literature has also contributed significantly to this imagery. Writers such as Arthur C. Clarke, Stephen Baxter, and Larry Niven have created stories in which entire civilizations attempt to survive the approach of a black hole, exploring themes of adaptation, sacrifice, and human ingenuity. Some of these works imagine scenarios where planets are moved from their orbits using colossal technologies, or where space colonies are launched away using the gravity of the black hole itself as a slingshot. Even the most fantastical fiction, however, often preserves a common trait: the notion that black holes represent insurmountable limits for science and survival. In almost all stories, encountering a black hole implies extreme decisions: abandoning the home planet, sacrificing part of the population to save others, or facing death itself in the hope of discovering what lies beyond the event horizon. Interestingly, fiction also tends to exaggerate the visual aspect of black holes. In reality, a solitary and inactive black hole would be almost invisible, detectable only by indirect effects. But in cinema and illustrations, they are often shown as bright, colorful vortices surrounded by light and turbulent matter. This artistic choice helps create visual and narrative impact, but reinforces a myth that there would always be something visible revealing the presence of a black hole. By observing what fiction has already imagined, we see that although the portrayals range from scientifically rigorous to purely imaginative, they all share the same fascination, that these cosmic objects are more than astrophysical threats. They are metaphors for the limits of human knowledge and the inevitability of facing the unknown. Although the idea of a black hole dangerously approaching Earth may seem at first glance like a purely fictional plot, astronomy has already identified real cases that, while not posing an immediate threat, demonstrate that these objects are not confined to distant, unreachable regions of the galaxy. One of the most notable examples is the wandering black hole identified in the Milky Way, located about 5,000 light-years away in the direction of the constellation Sagittarius. This object was detected not by emitting light, something impossible for an inactive black hole, but through its effect as a microlensing gravitational lens, a phenomenon in which the gravity of a massive body bends the light of a background star, temporarily increasing its brightness. By carefully analyzing this event, astronomers realized that the object in question could not be a star, as there was no visible or infrared radiation associated with it. Mass and motion calculations indicated that it was a black hole with about 7 times the mass of the Sun, traveling alone through interstellar space. Another intriguing example is the Cetus VFTS 243 system, discovered in 2022 in the Large Magellanic Cloud, a neighboring galaxy. It is a stellar black hole orbiting a blue supergiant star. While not a wanderer in the strictest sense, it proves that black holes can exist in stable binary systems without obvious signs of activity, meaning they can go unnoticed for long periods until an accretion event reveals their presence. There is also the case of the Kiowa closest black hole ever detected, identified in 2022 and informally nicknamed Gaia BH18, located about 1,600 light-years away It orbits a sun-like star. What is most surprising is that this star appears to remain intact, showing no signs of losing material to the black hole. This discovery was made possible by extremely precise measurements from the Gaia mission, which detected the star's movement caused by the gravity of its invisible companion. These examples demonstrate that black holes are not just exotic objects hidden in the centers of galaxies. They are scattered throughout space, and some may be relatively close in astronomical terms. The difference between close and dangerous is measured in thousands or millions of light years, but on cosmic timescales, trajectories can change and distances can shorten. The fact that we have already detected wandering, silent black holes suggests that many others must exist, still invisible to our instruments. Detecting a truly dangerous case would depend on identifying these subtle signals, such as small changes in the light of distant stars or deviations in the orbits of bodies in the solar system, before the approach became irreversible. These discoveries reinforce an uncomfortable truth. Black holes are not just theoretical concepts or remote threats. They are an active part of the cosmic landscape around us, and some are already at distances that, while safe for now, remind us that the universe is a place in constant motion and change. At the center of the Milky Way, about 26,000 light-years from Earth, lies one of the most impressive and influential objects in our galaxy, Sagittarius, a star, a supermassive black hole with approximately 4 million times the mass of the Sun. Despite its colossal scale, it remains relatively calm compared to active black holes in other galaxies, which emit massive amounts of radiation due to intense matter accretion. In the case of Sagittarius A star, current activity is low, but its gravitational impact on the structure and dynamics of the galaxy is deep and constant. The presence of a supermassive black hole at the center of the Milky Way is not a cosmic rarity. In fact, almost all known galaxies host such a giant in their core. These colossi seem to have played a crucial role in the formation and evolution of galaxies, influencing star birth, regulating the amount of gas available for new systems, and even shaping spiral arms. Sagittarius, A star, therefore, is not just a passive spectator, but a structural component essential to our cosmic home. The most compelling evidence for the existence of Sagittarius A star has come from decades of observations of stars near the galactic center. Some of these stars, such as the famous S2, follow extremely fast and elliptical orbits, completing a revolution around the black hole in just over 16 years. By measuring the speed and trajectory of these stars, astronomers were able to calculate the mass of the central object with precision, concluding that only a supermassive black hole could explain such gravitational strength in such a compact space. Although it is at a safe distance from Earth, Sagittarius A star has gone through more active periods in the past. Studies of residual radiation and nearby gas clouds suggest that a few million years ago, it released jets and bursts of energy capable of affecting significant regions of the galaxy. If similar events occurred today, they could generate detectable changes in the cosmic radiation reaching Earth, although they would not pose a direct risk of destruction. In the context of a black hole approaching Earth, Sagittarius A star has an indirect but relevant role. It is, in a way, the gravitational anchor of the Milky Way, around which our entire galactic system orbits. Changes in its stability or interactions with other supermassive black holes, something that could happen in galactic collisions, would have immense repercussions. Although such events are rare and occur on billion-year timescales, they could redistribute entire stars and planetary systems, including ours. Sagittarius A star also serves as a natural laboratory for science. By studying it, we can better understand the mechanisms governing the formation and evolution of black holes, and test predictions of general relativity under extreme conditions. This knowledge is vital for identifying and better understanding threats from smaller, closer black holes, such as the hypothetical intruder in our scenario. Therefore, although Sagittarius A star does not pose an immediate risk to Earth, it is a reminder that we live in a galaxy shaped by the gravity of an invisible giant, and that understanding this giant is an essential part of our preparation for dealing with any cosmic visitor of a similar nature. While the physics that describes black holes is so extreme that it inevitably sparks speculation about possibilities that challenge our traditional understanding of the universe. Among these ideas, two stand out for their fascination and controversy: time travel and the existence of alternative realities. Although so far there is no experimental evidence that they are viable, these hypotheses naturally arise when we explore the limits of the equations of general relativity. The theory predicts that space and time form a single fabric, space-time, and that this fabric can be distorted in radical ways by extremely large masses, such as those of a black hole. This distortion is so intense that, near the event horizon, time for someone outside and for someone inside flows in drastically different ways, an effect already confirmed by indirect observations and known as gravitational time dilation. In a limited sense, this is already a form of time travel. An astronaut who orbited close to a supermassive black hole and returned after a few years could find Earth centuries or millennia older. However, the idea of traveling to the past is much more complex and speculative. Some mathematical solutions to Einstein's equations suggest that certain types of black holes, especially so-called Kerr black holes, rotating ones, could contain structures known as wormholes, theoretical shortcuts in space-time connecting two distant points or even two different moments in time. If such wormholes existed and were stable, they could allow travel to the past or to parallel universes. The problem is that, as far as we know, they would be unstable and collapse almost instantly, unless kept open by some exotic type of matter with negative energy, something that has never been observed in nature. The notion of alternative realities associated with black holes is also linked to bold hypotheses. One of them is that the interior of a black hole could somehow be connected to another region of the universe, or even to a completely distinct universe, forming what some call an Einstein-Rosen bridge. In this scenario, crossing a black hole would not simply mean being destroyed by the singularity, but emerging in another point in space-time. However, even this optimistic vision faces a fundamental problem. Known physics indicates that any matter crossing the event horizon would inevitably be crushed by tidal forces before reaching any hypothetical exit. These ideas, though unproven, are extremely valuable to science. They help us test the limits of our theories, exploring scenarios where general relativity and quantum mechanics must be reconciled, something we have not yet been able to fully achieve. More than that, they inspire popular imagination, fueling stories, films, and research that keep the interest in studying these extreme phenomena alive. In the context of a black hole approaching Earth, time travel or escape to another reality would at best be theoretical resources with no immediate practical application. But as a research horizon, these hypotheses keep alive the hope that one day we may understand enough to manipulate space-time in ways inconceivable today, and perhaps find in the black hole itself not only an end, but a passage. Among all the mysteries surrounding black holes, few are as intriguing and debated as the information paradox. This dilemma arose from the combination of two of the most successful theories in physics: the theory of general relativity, which describes gravity and space-time, and quantum mechanics, which governs the behavior of subatomic particles. When applied together to the case of a black hole, these two theories come into direct conflict, raising a fundamental question: what happens to the information about the matter that falls into a black hole? In classical physics, information about an object, its composition, state, energy, and structure, could in principle be destroyed or forgotten. But according to the laws of quantum mechanics, this information can never be lost. It can be transformed, scrambled, or hidden, but it always exists in some form in the universe. The problem is that if something crosses the event horizon of a black hole, general relativity predicts that it will inevitably be crushed in the singularity, and that nothing, not light, not particles, not information, can escape. This suggests that the information would be lost forever, a direct violation of quantum mechanics. The situation became even more complex when, in 1974, physicist Stephen Hawking showed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon, in a phenomenon now known as Hawking radiation. This radiation leads to the gradual loss of a black hole's mass, causing it to eventually evaporate completely over the course of trillions of years. But if at the end of this process the black hole disappears and everything it swallowed was lost to the singularity, where would the information that, according to quantum mechanics, should still exist be? This is the essence of the information paradox. Either we accept that information is destroyed, violating quantum mechanics, or we discover that our understanding of black holes is incomplete. Since then, several hypotheses have been proposed to resolve the impasse. One of them is the holographic theory, which suggests that all the information about what falls into a black hole is preserved in the event horizon itself, encoded in a two-dimensional way, like a hologram that describes the interior. Another possibility is that Hawking radiation, although seemingly random, subtly carries the encoded information, allowing it, in principle, to be reconstructed. There are also bolder ideas, such as the notion that information is not lost because, upon crossing the event horizon, matter is transferred to another universe or region of space-time. Despite decades of debate, there is no definitive consensus. The information paradox remains one of the greatest enigmas in theoretical physics, and solving it may be the key to uniting general relativity and quantum mechanics into a single, comprehensive theory of quantum gravity. In the context of our scenario, a black hole approaching Earth, the information paradox raises an even more unsettling reflection. If our planet were swallowed, would all of humanity's geological, biological, and cultural history be lost forever? Or would it somehow remain inscribed in the depths of the event horizon? The answer, for now, remains as hidden as the interior of a black hole. For a long time, it was believed that black holes were eternal, perfect gravitational wells, capable of trapping everything that crossed their event horizon and existing indefinitely in cosmic time. However, in 1974, Stephen Hawking presented a groundbreaking discovery. Black holes can in fact die. This process is slow, almost unimaginably long for large black holes, but it is real and is linked to a phenomenon known as Hawking radiation. Hawking radiation is a quantum effect that occurs in the vicinity of the event horizon. In the quantum vacuum, pairs of particles and antiparticles are constantly appearing and annihilating each other in extremely short intervals. Near the event horizon, extreme gravity can separate these pairs. One particle falls into the black hole, while the other escapes into space. For an outside observer, the escaping particle is perceived as radiation emitted by the black hole. The net effect is that the black hole loses a tiny amount of mass with each emission, as if it were slowly evaporating. The time it takes for a black hole to evaporate depends directly on its mass. For a supermassive black hole like Sagittarius, a star, this process would take trillions of years, far longer than the current age of the universe. Smaller black holes, especially the hypothetical primordial black holes, could evaporate much faster and might even have already disappeared since the dawn of the cosmos. At the end of its life, as it loses mass, the black hole heats up and emits more intense radiation, leading to a final moment of massive energy release comparable to the explosion of millions of nuclear bombs in a fraction of a second. This final breath of a black hole, although unimaginably far in the future for the large specimens we know, is a reminder that even the most powerful structures in the universe are not eternal. On the cosmic timescale, black holes are long chapters, but not infinite ones in the history of space-time. In the context of an encounter with Earth, the death of a black hole would bring us no relief. Even a small black hole would have a lifespan far greater than that of our civilization, and a supermassive one would survive for absurdly long time scales. However, understanding that they also have a life cycle helps us put our vision of the universe into perspective. Nothing, not even the deepest gravitational well, is immutable. The study of black hole death is also directly linked to one of the greatest goals of theoretical physics, uniting general relativity and quantum mechanics. Hawking radiation is one of the rare phenomena that depend on both theories at the same time, and fully understanding this process could bring us closer to a unified theory of quantum gravity, a breakthrough that would forever change our understanding of the cosmos. Imagining the departure of a black hole that had passed dangerously close to the solar system is, in a way, just as intriguing as imagining its arrival. Although its retreat would mean the immediate end of the gravitational and radiative threat, the damage left behind would not vanish with it. The universe has no reset button, and the mark of its passage would remain engraved in every orbit, every planet, and even in the very structure of Earth itself. The first consequence would be the residual gravitational chaos. During its passage, the black hole would have profoundly altered the orbits of planets, moons, asteroids, and comets. Even after leaving, These new trajectories would persist. Planets that once had almost circular orbits could now follow extreme elliptical paths, leading to drastic temperature variations throughout the year. In more severe cases, some worlds might already be on their way to being ejected into interstellar space, becoming rogue planets. On Earth, if we had survived, we might be facing a radically different climate. Small changes in the distance from the Sun, or in the tilt of the rotational axis, could render certain regions uninhabitable. Oceans might have shifted in level, and ocean currents essential for climate balance could be disrupted. This would mean decades or even centuries of instability before a new climatic equilibrium could be established, if it ever could. Another legacy would be the late bombardment of celestial bodies. By disturbing regions such as the Oort cloud and the Kuiper belt, the black hole would have sent countless asteroids and comets toward the inner solar system. Even after its departure, these objects would continue to arrive, some taking thousands of years to complete the journey to us. Thus, the danger of devastating impacts could persist for generations. Gravitational instability could also create new planetary configurations. Moons might have been torn from their planets and captured by other bodies. Asteroids could have become temporary satellites of Earth or other planets, creating new collision risks. These rearrangements would change not only the dynamics of the solar system, but also the appearance of the sky as we know it. From an astronomical perspective, the black hole's departure would give us the opportunity to study its effects in unprecedented detail. Telescopes and probes would record changes in orbits, the behavior of displaced matter, and even the dissipation of any accretion disk that may have formed during its passage. This knowledge would be invaluable for predicting and mitigating future encounters with similar objects, although on a human timescale, the likelihood of surviving two such events would be minimal. Finally, there would be the psychological and cultural impact. Humanity, having survived such an immeasurable cosmic threat, would surely change its perception of its place in the universe. Our fragility and dependence on stable astronomical conditions would become even more evident. It is possible that, after such an event, entire civilizations would direct more resources and efforts towards space exploration, seeking new homes and ways to protect themselves from the unpredictable. In short, if the black hole were to leave, it would take its crushing gravity with it but leave behind a profoundly transformed solar system, a more unstable, dangerous, and unpredictable place in which life would have to adapt or disappear. Thinking about the approach of a black hole is, above all, an exercise in cosmic humility. These objects are not conscious enemies nor forces that chase us. They simply exist, inevitable products of the physics that governs the universe. But their mere passage, even without a direct collision, would be enough to rewrite Earth's history or erase it forever. Faced with something like that, it becomes impossible to sustain the illusion that we control our destiny on cosmic scales. The black hole is the ultimate symbol of how the universe can be both beautiful and relentless. It reminds us that the order and stability we experience here are exceptional, not eternal guarantees. For billions of years, Earth has remained in a delicate orbital balance, bathed in the sun's light and protected by its gravity. But a single wandering cosmic intruder could dismantle this harmony in a matter of days, or even hours. This awareness, far from provoking only fear, can serve as a call to responsibility. By understanding our vulnerability, we realize that scientific knowledge is not an intellectual luxury. It is a vital tool for survival. Early detection of threats, the study of extreme phenomena, and the development of mitigation technologies are not tasks that can be postponed indefinitely. The history of the universe will not wait for us. There is also, in this hypothetical scenario, a deeply philosophical aspect. If a black hole truly came and we could do nothing to avoid it, our response would depend not only on science, but also on what we choose to preserve and pass on. What records would we leave? What values would we uphold in our final moments? Would we be able to face the inevitable with dignity, knowing that we are witnessing a natural phenomenon and not a tragedy unique to Earth? In the end, the approach of a black hole is more than an astronomical disaster. It is a reminder that we are part of something much greater, a vast, dynamic, and impersonal cosmos. Our existence, fragile and brief compared to cosmic scales, is sustained by incredibly specific conditions that can change at any moment. But perhaps it is precisely this fragility that gives meaning to our presence here. Knowing that the universe is indifferent to our survival can inspire us to value the time we have, to explore with more courage, and to care more attentively for our small blue dot. Because in the end, while we cannot control the movement of stars and black holes, what we can control is how we live under the fleeting light of our sun. And do you think humanity would survive a black hole? Or rather, will humanity even remain alive until then? Leave your thoughts in the comments and tell me which city you're watching from. I'd love to know how far the channel's videos are reaching. Sweet dreams, and see you in the next video.